let's talk about functional form. We have said that our garden variety regression model is linear, and we always write it that way. And what's the sense in which we mean that the model is linear?
First order.
I don't know what that means.
That the dependent variable.
Oh, what you mean to tell me is that this straight line is a first order approximation to whatever it might be. Oh, okay. And that's fair enough, but that's not the sense. That's not the answer that I was looking for. So maybe if I try this way, what are the senses in which that's linear? Y equals A plus Bx. What's a little disturbance?
Is it because B is a constant?
B is constant. We would say that it's linear in x and y. Alternatively, we could say that it's linear in y and the coefficients. Since the coefficients aren't known to us, the x's are known. The y's and the x's are known, and the a's and the b's are not. So alternatively, we could think of this as being linear in the variables, the y's and the x's, or linear in the unknown coefficients. Fortunately for us, in applying least squares, all we need to know is that the model that we're after is linear in the unknown. We don't have to stick with just straight lines. There are many curved lines to which we can fit our data, which are linear after a suitable transformation in the unknowns, the alphas and the betas. So for example, suppose that you had some data on x and y, and I don't know why this is going on. Figure 1 got separated from its caption a little bit. Suppose you had y and x. The curve that's plotted in the figure is y is equal to alpha plus beta times the log of x, just a semi-log. And you got a nice smooth curved line. But y is equal to alpha plus beta log of x is still linear in the unknowns. Okay, so right away, immediately, you can see that we don't need to maintain the notion that things are linear in the data. It can be linear in the parameters that we're trying to guess. If we did it in log-log, depending on our choice of beta, we would get a line that's convex or one that's concave. And by fitting our data to the log-log form, we could allow the data to determine whether or not the relationship between y and x is concave or convex, without knowing beforehand which it really was.
So you would say in the second case that it's still linear in the unknowns?
Still linear in alpha and beta, yeah.
Okay.
The dependent variable now is the log of y. At the time that you press the OLS button, does the computer know that you've taken the log of y and the log of x? No. It just sees some numbers in the memory registers. And it works with the numbers that you put in the memory registers. But you remember that the numbers that it's working with are logs. You could take anti-logs, right, and go back to the true underlying function. But as long as you could transform the true underlying function into a form which is linear in the unknown parameters, you can use OLS. If we change the sign, so this is an example in the first panel. In this case, beta is positive. In the next panel, we can just change the sign on beta. Or, if you change things, if you impose different sets of restrictions, you can get one that approaches a horizontal asymptote. Who in here is estimating the demand for money? Right? You've read all about the liquidity trap, right? And that's a big controversy in macroeconomics, whether or not there's really a liquidity trap, right? I think that's part of the remember all these things. So here would be an example where you're estimating and trying to figure out the liquidity trap, where it is. So you might use this kind of functional form to do that. So we're only limited by, so this, by the way, is y is equal to alpha plus beta times 1 over x. Or you could flip things around and do it the other way. So you're only limited by how creative you are. You could get a nice parabola. And at the time of estimation, you can decide whether it's concave or convex, just by fitting a quadratic form to your data. So we're not limited to a world of straight lines. We can get lots of curvature in the world. We can fit a cubic and get all kinds of different curves out of that cubic. Let's fit the data one way or another. In every case, we say that these specifications are parametric. That is to say, there are closed form representations of the line, so that the representation of the mapping from x to y is done the same way for every value of x. And you have a simple functional representation from one to the other. There are other techniques that we'll talk about in the spring. So an alternative, a non-parametric approach to fitting nonlinear data is so-called kernel regression. That way, you don't ever know the functional form between x and y. Just local weighted averages, basically. So your best prediction for y becomes a local weighted average of their x's.
Kernel?
Yeah, kernel, K-E, not like Colonel Sanders and
Yeah.
K-E-R-N-L. K-E-R-N-E-L.
Yeah.
Remember that beta hat is x prime x inverse x prime y. So beta hat is just a weighted average of the observations on the y's. And the weights, the rule for constructing the weights is always the same, and it's linear in y. Beta is linear in y. But who's to say that that has to be the case? Why not come up with a rule where the weighted average of the y's depends on the particular neighborhood of x that you chose? And the weights change as you move along. And because it's just a locally weighted, instead of being a weighted average of all the y's, it's just a weighted average of the local y's. So that way you can get very highly nonlinear shapes to fit the data. Just to show you an example where I was doing this recently. I'll give you an example of using the kernel method. What we have in the picture is, on the right, on the horizontal axis, it's kilograms of biomass of animals that run on the ground that were brought to market in the city of Malabo in Equatorial Guinea. On the island of on the island where Malabo is located, people eat wild animals as food. They go out in the forest and they shoot things, or they trap things that run around on the ground, and they also hunt things that live up in the trees, like different kinds of monkeys. And they eat them. So the horizontal axis measures the kilograms of animals that live on the ground who are running around in the forest and got captured and came to market to be consumed. And the vertical axis measures kilograms of animals that live in the trees, arboreal animals, like monkeys, and a small number of birds, but by the vast majority, it's monkeys that come to market. And so a given G and A pair is the kilograms of ground animals and arboreal animals that came to market on a given day. So that, for example, this data point is about 125 kilograms of ground animals came to market, and about like 75 kilograms of monkeys came to market to be eaten on that day. Now, the people who bring these to market are hunters. They have production functions. They go out in the forest, and if you're busy shooting off your gun killing monkeys, you're going to scare all the ground animals away. So there's a trade-off between your production of ground animals and your production of monkeys that you're going to bring to market, because it's production possibilities. And you know from principles of economics that when you plot the combination of outputs, you should get the production possibilities function, right? So the old guns and butter trade-off. So now the hunters in the forest are confronted with an arboreal ground animal trade-off.